Right, so this is going to be known as the Michael reaction. And basically what we're going to do is basically use a less basic, less nucleophilic enolate to act as our nucleophile, and then it can attack our electrophile in a conjugate addition. So for example, if you had this compound right here, and then you added some base to this, right? This proton right here is going to be the most acidic proton, and so that's what's going to be deprotonated. So we have a negative charge there. And then if you think about this negative charge, this is kind of doubly stabilized by resonance. It can resonate with the carbonyl on the left and the carbonyl on the right. So it's more resonance stabilized than your standard enolate. So it's going to be less reactive. And since it's got less reactive, it's a weaker nucleophile, weaker base, we're going to prefer our conjugate addition over our direct addition. So this is one way to push towards that conjugate addition. So the overall reaction scheme is going to look something like this. You're going to have some kind of carbonyl that, if deprotonated, is doubly resonance stabilized. You're going to add some base to deprotonate it and make it a good nucleophile. So for example, here we're going to add some sodium ethoxide because we've got ethoxide here, and that way we don't mess with it. That'll form your doubly stabilized anion. And then after we have that doubly stabilized anion, we can then add our alpha beta unsaturated carbonyl. In this case, I'm going to make it a very simple ketone. And then this is going to go ahead, act as our nucleophile and do the 1,4 addition. So it's going to attack there. And then after that, we're going to get some tautomerization and some proton transfers. And this will be assisted by our acidic workup to form our final product over here. Cool. So what you'll notice is that this double bond is now gone, right? And then this carbonyl is still here, right? It got turned into the enol form and then retautomerized back to its ketone form. Overall, over here, we call this guy the nucleophile, is known as the Michael donor. And then this over here, our electrophile, is called the Michael acceptor. So you can see with the donor, we want something where the negative charge is going to be resonance stabilized, and the acceptor is just going to be some kind of alpha beta unsaturated compound. So here's just a list of some donors and acceptors. Right, there's that double resonance stabilization. We can have turn one of them into an ester, or turn both sides into an ester if we wish. We can also use some derivatives, some carboxylic acid derivatives, such as the cyano group, that also can undergo resonance stabilization. Or you can just use a nitro group as well. That nitro group is very electron withdrawing, so it really helps stabilize that negative charge. Right, so all of these donors, they're all have a resonance stabilized anion. And they're all acting as the nucleophile in our reaction. For the acceptors, it's just various types of alpha beta unsaturated carbonyls and some derivatives. So you can have aldehydes, you can have ketones, you can have esters, you can have amides, you can have the cyano group, or you can just have a nitro group.